Okay, so for the last like 15 months, I've been working with GFR, and what we're working towards is something like what you're seeing here. Let me just speed this down, or will it let me?
Oh, what is GFR?
Global Formula Racing.
Okay.
So what we're aiming to do, right, is just build a car that is an electric autonomous vehicle. Let me also,
Mm-hmm.
that's too late. You guys don't get a video of me, sorry. Um, but yeah, it's just this. So there's no guy driving this car, no girl driving this car. And the
Mm.
track is defined on the right by yellow cones, and on the left by blue cones. And there's a total of 4 different classes of cones that we need to detect. And then also label in 3D space relative to the car. So you can see this is what most of these object detection systems do, right? Is they put this bounding box around the things of interest. So this is just to give you, why, I'm building a cone detector. Why are we building a cone detector? We want to race a car around a track without somebody driving it.
Mm.
So let's look at the high level design goals here that we got to meet.
Mm-hmm.
This cone detector needs to be energy efficient, computationally efficient, needs to be fast. So we're going to measure that in frames per second. We want at least 10 frames per second, given how fast the top speed of the car is. That's what dictates that. And then it would be nice to have position estimations too. So if we detect a cone, we want to know not only where it is in the 2D image, but where it's located in 3D space relative to our vehicle. The first 2 points are nice. You can think of it like a trade-off. If we can spend less energy computing and finding all these things, that's more energy that can go towards moving the car, since it's an all-electric vehicle. We can go faster or longer distances. And then this cone detector isn't the only thing we need to run. We need to run a lot of other modules of software. And this is on sub-desktop performance hardware. So that's what we'll touch on next, is what we're actually running all of this on. And so it's the main compute unit is called the NVIDIA Jetson Xavier. And so this is what you would get if you took something like a Raspberry Pi here and you give it steroids.
Mm.
Okay, so this is actually pretty close to scale if you know how small these Raspberry Pis are. This maybe should be a little bit bigger.
Mm-hmm.
But there's a carrier board here on the bottom that in some applications you can remove. We're going to need it as seen here. And then this is a big cooler on top.
Mm.
But this guy's pretty beefy. It's got an 8-core ARM processor, so that's something you'd have in like a high-end phone. It's got 32 gigabytes of RAM. It actually has a GPU on it. It's got 512 CUDA cores, so that's really nice. So we can write these, deep learning loves being done in parallel. And it's also got these ASIC chips. So these are kind of like TPUs, in that they're energy efficient and they're specifically built for matrix multiplication. NVIDIA calls these deep learning accelerators, or DLAs. And so both of these, it's hard to compare these DLAs to the GPU, but we'll say they're roughly equivalent, the two combined, and they only run on a combined like 8 watts. So that's awesome for our applications, especially considering we actually run multiple softwares, multiple deep learning models. And so here's our first one. The second one's a little easier, but this we kind of need to go in order. This one detects where our cones are in the image. And so this is YOLO, the version 3 network architecture. Maybe people have heard of this. Anybody familiar with this?
Yes. Yep.
Yeah.
Okay.
It's pretty fun. So it's hard to know how much detail to go in with describing this, but I'll just take a whack at it. So this is this is pretty standard deep convolutional neural network stuff. So these residual blocks will just be, your convolutional layers, your max pooling, your average pooling. This is like, oh yeah, you can see. So this is compressed. This is 35 layers of skip connections and residual blocks. And then something you'll notice is we actually have 3 output layers. So we'll do some computation from the input, crunch some numbers, and then we branch off and we get our first output, which is a
Mm-hmm.
small tensor. And then what we'll do is this is an upsampling layer. So this is just like zooming in on an image, right?
Mm-hmm.
And then we'll do some more computation. And the other thing of note is like these are skip connections. And so this is, you can kind of think of it as these skip connections are to ensure that when you get really deep, you don't lose kind of the global context. The idea is that this information is useful to have and you don't want to lose it.
I see.
It probably helps with being differentiable too, you know, that's
Uh-huh.
the idea behind residual nets in general.
Right.
But yeah, so going back, we got one output and then we'll keep processing and we'll come up with another output. And we'll do this again kind of, and we'll get 3 outputs. And these layers are called YOLO layers. And they're just, this is ultimately the tensor you parse. And this tensor represents your bounding boxes in a grid. And the only thing that's changing between these 3 different guess layers is how coarse or fine that grid of guesses is. So you can see here at the end, this is the biggest tensor. This is where you actually detect the most cones. You know, if all of these were fully saturated and it was finding as many cones as it ever could, this would always be the most cones here.
Mm-hmm.
And then if you understand that, the last thing that kind of happens is you can actually get multiple cone guesses in one layer that guess at the same thing. Like maybe we have 2 cone guesses here at this dog at this layer that are actually, you know, we really just want one. And it can even get worse. You know, maybe this layer is also guessing at a dog too. So you've got 3 boxes that you need to aggregate into one guess. And that's done by the final layer called NMS. It's just non-max suppression or something like that. And that's one of the weak points of this algorithm, especially because false positives are so detrimental to this type of application, you know. But
So
yeah, go ahead.
there are in fact more than one cone, or is it getting confused?
Yeah, that's the trade-off with one of the hyperparameters of NMS. It's based on threshold of overlap.
Mm-hmm.
So if you set your overlap, you know, if you set this, I can't remember which way, but I'll just, you know, if you set it too high, you run the risk of labeling one cone with 2 boxes, which would indicate to our system, hey, there's 2 cones here, when really there's 1.
Right. Okay.
And then the other way is there are actually 2 cones there, but you label it as 1 cone. In the final slide, there's in my extra slide, I talk about DETR, D-E-T-R, which is a Facebook algorithm, which would be interesting for us to check out because it uses like attention from NLP to kind of solve this. And to make sure that there really is only one guess. The problem with that is computational tractability on this type of hardware. Okay, so that's how we do it.
Question.
Yeah, go ahead.
Yeah, so have you looked at YOLO V4 as well?
Yes.
Because that is, and so one of the other questions I had is at the beginning you mentioned like your inference goal is 10 frames per second. So in your framework, the way I understand is, are you doing sequential frame processing or are you doing it? One of the techniques I was thinking is if you want to increase your inference speed would be to do some kind of asynchronous processing. So what I mean by that is as you're operating on your current frame, this YOLO V3 or V4, you obtain the next frame and that way you reduce some of the time for inferencing. Is that an approach you're also looking into?
Yeah, sometimes if our processing, I think it's mainly sequential. Sometimes, you know, if it takes too long and we get a whole bunch of frames, we'll drop them. Otherwise, you know, that becomes just kind of a bottleneck. I looked at V4 when it first came out, and they've actually even got V5 out now. But I think they're all 3, 4, and 5 are different authors. And I wasn't too impressed going from 3 to 4's performance, and I really haven't looked at 5. there's some things we're trying to still solidify in here, like some of these last layers, these YOLO layers, are still done. I mentioned the DLAs, the deep learning accelerator chips on this. The only way to program those and to have access to those is to use another deep learning library that isn't too popular called TensorRT. And they don't have a full implementation of YOLO. That doesn't include some
Okay.
Python post-processing.
Mm.
And so the idea being we could go to V4 or V5 of YOLO, but first it'd be nice to kind of get the real improvement game right now for us would be more so to make sure we move everything that should be on the GPU to the GPU so we can take full advantage of it.
V4 and V5 are more towards adding new tricks from vision rather than actual conceptual improvements. So the original author stopped working in vision after V3.
Yeah, he started going
So
into ethics or something.
yeah, because of the ethical implications in vision, he just stopped working in vision altogether.
Have you guys ever seen that guy's?
Resume is the best, yeah.
Yeah, that's what I was thinking of. Thank you. He's got a brony artwork like My Little Pony all over it. It's really a trip. So that same mind came up with this. So I don't know what that says. Okay, so that's the hard part. The other bit is once we've got the cones from YOLO, we will force each cone. We'll kind of resize it to 80 by 80, something like that, 80 by 80 pixels. And then we throw it through this fully convolutional layer, or network rather, called RecNet. So this is from MIT, and you can see MIT's car here. I think it looks really cool. But yeah, this is just convolutional layers and skip connections. So this thing is very fast, especially on either the DLA or the GPU. And what this is doing is it's really just regressing 7 2D points. And so this is supervised learning just like YOLO. So you get a whole bunch of these cone images and you mark them. And then we just used SGD to train it. They incorporate some geometric priors via a regularization term. So this is, they expect, independent of where this car is in 3D space, that this angle should hold here between these two straight lines. So you use the dot product and vector norm to calculate that. And so if it's not the ideal, if the guesses that your model trains aren't ideal and don't fit this geometry, then you can punish it and give it higher loss. And it's the same thing over here. These lines should be parallel. So you just construct them and use the dot product and place that in your loss.
That's interesting.
Any questions on this?
So did anyone try to simplify this, and did they show that all these YOLO layers are needed?
In the previous one?
Yeah.
Here, let me go back. Has anybody tried, so like trying to do maybe an ablation study or something like that?
Yeah.
I don't know. I can't speak, not that I know of, but I would not be surprised.
Yeah, it looks kind of overly complicated, but I'm sure that there are reasons to.
Yeah, the pyramidal thing, I forget the logic behind this, but really it's like this has been shown to be good, like to catch big images, medium-sized images, and then small images.
I see.
The deeper you go in processing.
Right. So the RecNet one is completely different, or is it kind of built on top of the previous?
Yeah, you can think of it as just an extra bit. YOLO will spit out these kind of regions of interest with individual cones. And then so each cone we get from YOLO will pass through here. And it's not even fully differentiable end to end. Like we train both of these systems independently and then stack them on top of each other.
So what do you do with the multiple layers in the YOLO?
We aggregate them with, so that spits out 3 outputs. What do we do with them?
Yeah,
we aggregate them, and then kind of the NMS thing looks and sees how much overlap there is, and we'll aggregate some guesses into one guess, and then that's it.
I see.
And then what you can do with these points, since we're working in 3D space, you know, you can use. I'm not too intimately familiar with the linear algebra of this, but if you know some of the they call them intrinsic parameters of your camera, right? You know how much it warps space or whatever.
Right.
Warps your image view. Given 4 points, you can actually predict where this is in 3D space relative to your car. And then the extra 3 points you can actually use for like outlier detection. Essentially, look at different combinations of the point to kind of get a sense of what the true answer is. Like some of these points you'll see can just be way out in left field that make no sense.
Right.
Okay, so this is from the MIT paper. So they've got, let's look at that car one more time. They've got a whole bunch of cameras here. I don't know if all of these are cameras, but at least 3 of those are cameras. And why this is important is they use 2 of those cameras to get stereo depth. So that's really easy. Well, not really easy, right? But that's how they get the 3D position. And those 2 stereo cameras go way further out than the mono camera setup. And so for all these points, they get depth from, yet again, the linear algebra of the intersection of 2 cameras. But up close to the car, they've got this camera angled down. And this is what they'll actually, since they don't have the stereo depth math to guess the 3D position, this is where they'll use these 7 points to guess.
I see.
And the error, you know, it's tough to make it out. I mean, about 30 feet from the car here, 10 meters, they're at an average of about a foot inaccuracy, you know, a foot of error, which all things considered, I think that's pretty impressive. Okay. And now that we've kind of built them, this was April of last year. These are our results. We've got them running actually on the car on the Xavier. Real low memory. It wasn't really concerned, but it's nice that all this is running on less than even 100 megs. And this is a lot. We can see these are all floating around 30 frames per second, whether it's on the GPU, whether it's on the deep learning accelerator chip, or whether the precision is floating point 16 or int 8. So this is like integer 8-bit precision, so just like a char. And then RecNet runs like it's on fire because it's just all convolutional layers.
I see.
And it's really fast. But if you think of it, YOLO takes in an individual image and will actually output potentially like 20 cones per image, right? So it makes sense that RecNet actually needs to run very quickly.
Right.
Yeah.
So you're running RecNet on each cone.
Yes.
So
we might call RecNet like 20 times per individual image we give to YOLO.
Okay.
And then one other thing to notice about this slide is even though it says on the DLA, there should be like a star here. The YOLO model is too big to fit on the DLAs. So some of the layers still end up on the GPU.
I see.
But YOLO's small, so this is like 60 frames per second, only 4 watts of like energy. And here's some, so the only difference between these 2 is going to be this one includes the RecNet dots, and on the really small far away cones, it really gets in the way. So that's why I've included this here on the left without them. But it does pretty good. I'll wait for one of these to give me a far away one, and we can like, oh, this one's really good. This will come up in the next scene or the next slide. But notice, you guys might not be able to tell, but can you go away there, buddy? This line of cones on either side stretches way out into the distance. And you can kind of get a sense of where YOLO stops being able to tell where these are. But this type of image presents, since this is supervised learning, this is a hard case of knowing what, you have to label the real answers, and it's really hard to label the real answers when they go off into the distance like this and they kind of merge together.
Right.
Okay, so let's So once we had some results, we could actually kind of, take a step back and see where the low-hanging fruit is again. And I noticed there's a lot of poor labels here. So you can see there's something funky going on here, right? This really isn't where the base of the cone is.
Yeah.
This is an opportunity for me to ask you guys to humor me. What would you guys do if you were asked to label cones in this image? Would you label the cone in this guy's hand or not?
By labeling, you have to mark the border.
Yeah, just draw a box like it's drawn here.
Okay. Yeah, it looks like the left-hand side, the overlap thing seems to be wrong.
Yeah, this is the YOLO guessing at it. And so
Mm-hmm.
YOLO went, okay, here's, there's a cone here, but if you go and actually find the data we trained it on, we didn't label this cone. So it's kind of like a mixed signal. And it's a really hard question, I think, when you got human in the loops for supervised labeling, like object detection like this.
Yeah.
If you asked me later tonight, maybe I'll give you a different answer on whether or not we need to label this.
Yeah.
And see, there's a partial cone here, and as a human, right, we know this cone exists over here, right? Object permanence.
Yeah.
So this is another one. It's like, well, do we just draw what we can see? Do we extend it off the edge of the image?
Right.
And then we talked about this one already, where they go off way in the distance. What do we do about these?
Right.
There's a lot of edge cases.
Yeah.
So
what happens if you miss one of these things, although it's kind of there?
Yeah, so that's the fortunate case of big data. It tends to learn even if you give it enough crappy data, poorly labeled data, it still will learn. But the underlying idea being a whole bunch of good quality data is even better.
Right.
And so we just took a really small subsample of our data set and cleaned up the labels and trained to convergent 3 times for each. And the old labels got 52.6% accuracy. And even on the small data set, the improved labels picked up 4.5% accuracy. So that's just, a quick sanity check that, maybe this is worth investigating later and putting in time into relabeling everything.
So
Sorry,
I suppose that even if you don't get everything right, it doesn't matter too much because you're just using it to navigate.
It depends for RecNet. If RecNet worked really good and we went with RecNet, yeah, it might not matter too much, especially if we overestimated the bounding box. But like the next slide, what I'll show is we might use LiDAR to both improve detection of cones and to figure out where they are in 3D space. And that would be a bigger issue is that we want really tight bounding boxes, as tight as possible, if we use something like LiDAR. Somebody else had a question?
Yeah, sorry, I had one last question. So I'm assuming you took the YOLO, which was already trained, and then essentially you're using RecNet and you trained on it. So is there a possibility that combining doing a joint training of the YOLO plus RecNet, like creating a network which combines both these, would it give you better performance?
I'm sure it would. That's something I hadn't really thought about, and maybe part of the reason is I'm still on the fence about RecNet.
Okay.
We'll have to do more experiments with it, but that's a really interesting thing.
Yeah.
Yeah, and I got the note here: humans in the loop suck. Okay, and I think this is our last slide. It looks like we're doing okay with time. Yeah. So I've also explored, we've got LiDAR on the car, and I'll talk about what LiDAR is in a minute. But the idea is maybe this can help if we fuse the camera data we've been talking about so far with the LiDAR, maybe we can get that position more accurate and detect cones better. And so what LiDAR is here's the abbreviation or the full thing, light detection and ranging. It's a technology that uses light in the form of a pulse laser to get 3D position, ranges as they call it here. So these LiDARs are notoriously expensive.
Looks like we are probably looking at your old video. Did you change the slide?
It looks like we're looking at what?
Looking at your earlier video.
Yeah, it's stuck.
Is anybody, oh, hold on. How do I exit full screen? Anything?
No, it's still the same.
Is anybody seeing like a whole bunch of blue image with green dots on the right? Anybody?
No, it's still a video.
Okay, hold on. I will try one more time.
Okay.
Okay, cool. I'll just keep it in this mode. Yeah, so LiDAR is expensive, notoriously expensive. Like just a couple of years ago, you would have to shell out tens of thousands of dollars. Now some of the OK units seem to be like in the $5,000 range, but they will have limited resolution. So you can see here on the right, there's a lot of gaps when you overlay them, and that just speaks to how much higher resolution RGB cameras are. And then they'll also have vertical fields of view cutoffs. So you can see here in the trees really easily, there's this sharp cutoff where you can't see anything above it. Waymo is Google's like autonomous vehicle company. They released a new data set where they overlaid these for you essentially, did all, like this isn't trivial. And just did a quick test on a subset of their data to see if this could do better than RGB detection. It worked pretty good, but it was hard to replicate. We failed to replicate this kind of test on our data because we've only got this old data and we don't know those camera intrinsic parameters. So it's pretty hard. It's a pretty laborious process to get this nice overlap of the two, like you have here on the right to train on. And that's pretty much it. I had this extra filler slide, but if anybody's got any questions, I'm happy to answer them.
Yeah, I just had a question about LiDAR. I know the quality of the LiDAR camera you use on these cars is very different from the ones which are available in iPhones or iPads, but how different are they? Because you do get an iPhone in like $1,000, so is the LiDAR on that bad as compared to this?
I'm not too familiar. I've never looked at it. I would assume it mainly, well, you don't get 360 degrees with the phone. Like this image, our LiDARs will actually do a full 360 degree view.
Okay.
Another, like if I were to Google this, I'd be interested in the resolution relative to ours, and then interested in the ultimate, the inaccuracies, once you get out to like 10 meters, they might have,
right.
I'm just guessing, right? They might have bigger error bars the further out you go.
Yeah, I was just wondering which parameter basically worsens, because definitely some of the parameters will worsen. So yeah.
I think it's really cool though. I honestly did not realize that they have those in iPhones. That is super cool.